So now that you've just got comfortable in thinking about the addition of a halogen, one of the things that I'd like to point out is it is possible to change the solvent. So in this next example in the teaching model number 4, you can see that I'm explicitly mentioning that the solvent is H2O. So to make the contrast, I'm going to go back now to these other examples here. And in order for this reaction to have occurred as such, we are assuming that the solvent here is something like carbon tetrachloride, so CCl4. And we're choosing a solvent that is not reactive and therefore won't be involved in, let's say, a second nucleophilic step. So in that case, I say the solvent is the carbon tetrachloride. And then indeed, of course, just to emphasize that the reason why it's the bromide that attacks at this step, the solvent once again is the carbon tetrachloride, which we can also call tetrachloromethane. And again, in this reaction, we assumed that the solvent was the carbon tetrachloride or the tetrachloromethane. However, in this section, we explicitly say that the solvent is water, and that changes things dramatically. In a sense, what we're saying here is that a halohydrin will form. So this comes out actually just by looking at the mechanism. So I've in part written it out here, and I've also written it out in your booklet. So this will scaffold writing out the mechanism a bit. As a matter of practice, the attack will occur at the more delta positive chlorine. And I'll make it that that's the chlorine that I've labeled with the lone pair of electrons. So this would be delta positive, this would be delta negative. Now we're going to have the attack of the pi bond at this more delta positive chlorine, and then we'll have the back attack, the lone pair of electrons, and then the breaking of the chlorine-chlorine bond. So as a result, once again, we have the chloronium ion. And I will emphasize that we do indeed have this chloride ion in solution. Now the thing is, it's either going to be water or the chloride that attacks. Now chloride, even though it's a very weak base, is actually a reasonable nucleophile. And water is a weak base, and actually, as it turns out, it's also a weak nucleophile. The thing is, it's the solvent. And what this means is that you've got a whole ton of it. It's everywhere. It's ubiquitous. And therefore, it's more likely that a water molecule is going to attack the more substituted carbon. So certainly we'll get minor products where the chloride will have attacked, and we'll get the trans dichloro product. But the more major product will be the result of the water attacking here. Once again, that bond will break, and as a result, we add the water on the opposite side of the chloronium ion. So once again, this is an anti-addition. We end up having the oxygen and the chlorine being trans to one another. Just like the acid-catalyzed addition of water, we can't stop at this stage. We do need to deprotonate our now protonated alcohol. And certainly because water is the solvent, it's going to be the best base that's present. And actually, in terms of comparing chloride to water, water is once again the better base. Recall that chloride is the conjugate base of a very strong acid. So even if water wasn't the solvent, water is still the better base here. So the alcohol group gets deprotonated, and now we have the product. So once again, in terms of the regiochemistry, we would say that the addition is Markovnikov. In terms of the stereochemistry, we would say that it's anti, and this reaction is stereoselective. Now, I combine these two reactions, that is the halogenation and the halohydrin formation, because essentially they're the same reaction. The only difference is it depends on what solvent that we have. So if your solvent is water, or if your solvent is an alcohol, you will get, instead of adding a second halogen atom, you will be adding either OH or O carbon chain. In other words, you'll form the ether bond. But it's the same general mechanism, and it's the same properties in terms of being Markovnikov and the anti-stereochemistry.